All right, so this is my Module 3 on coding and generalized linear models. So just in this model, we're going to be comparing general linear model and then the generalized linear model. So to go into the differences, in regular general linear model, this model utilizes ordinary least squares and it has to meet the Gauss-Markov assumptions. For example, we want to have normal distribution, independent residuals, homoscedasticity, and we'll see most importantly for our case, the dependent variable must be continuous so that we can have continuity across the range of our residuals. And over here in the generalized linear model, this is similar to OLS, but it allows for different distributions like binomial distributions. So it doesn't take into account the Gauss-Markov assumptions, which allows us to look at binary dependent variables that often aren't normally distributed. So one type of the generalized linear model is logistic regression, and that's what we're going to be running, as we'll see soon. So we're going to begin by just taking a look at our data. So we are seeing in this data which variables predict survival outcomes of horses. So we're looking at the dependent variable with this histogram, and we can clearly see that this is a binomial model. We can see that there are 2 survival outcomes, 0 for died or 1 for living. And because the mean of the variable is 0.6, this means that there's almost an even split in life or death. And so we can justify using logistic regression here. And what we can also see is that this data does violate that normal distribution curve because it doesn't have normal bell-shaped curves. So, all right. In explaining the data just a little more, we can see that we have 3 predictors, 2 of which are continuous, and then 1 is pain level. So this is a categorical variable with 4 levels. So alert, which is the most normal group, then mild, severe, and extreme pain. So looking specifically at this coding matrix, we can see how we went ahead and coded that categorical predictor pain. So dummy coding is the default in R. So when we set this factor variable, it is automatically dummy coded. And this just allows us to look at the mean comparisons between our base class and all other classes. So from this matrix, we can see that our comparison or our base group is alert. And we're comparing that to mild pain, we're comparing alert to severe pain, and then alert to extreme pain. So that's why we have 3 levels. So I conducted a multiple regression analysis on my model as well as a standard model. And we're going to see both of them listed here, and we'll go through the results of them in a bit. So what we're looking at is the main effect of pulse, body temperature of the horse, and then different pain levels on predicting whether or not that horse lives. So we also tested the interaction of body temperature and then on each of those 3 levels of pain. But before we jump into the results of the models, it's important that we kind of discuss what logistic regression is and how the parts of this model differ from the output in regular linear regression. So for one, the B's are not the same. So in logistic regression, the B's are log odds. And these B's basically allow us to see how much each one of those variables either bumps up or down these odds ratios. So because the B's are a little bit difficult to interpret, we can also take out the exponent to get an odds ratio. So this is basically the ratio of P over Q, where P is the probability that the event occurs, and then Q is the probability that that event doesn't occur. And then the law of total probability tells us that P plus Q equals 1. So in other words, all outcomes of this event must sum to 1. So ideally, we're going to want P to be greater than Q. Moving into the results now of the logistic regression, we can first note that we did center our variables by taking the means out. So that's why we see pulse C and body temp C. This was in an effort to reduce any multicollinearity, because multicollinearity in regression and logistic regression is a problem and it can never be solved hierarchically because it's estimated simultaneously for these types of categorical prediction. And this means that we do have to pay attention to an increased likelihood in type 2 error. So from looking at our first predictor, we can see that pulse significantly predicts the chance of survival for a horse. And we know that because the p-value is significant at the 0.05 level. And interpreting the regression coefficient for pulse, The B here is negative 0.011. So basically for every single point increase in pulse, the log odds of a horse's survival decreases by 0.011. And this is holding all other predictors constant. And then when we take that exponent out, we get this odds ratio. So this gives us 0.99. So for every single point increase in pulse, the odds of living decrease by 1%, holding all those other predictors constant. And we got this basically from taking the percentage by comparing odds ratios to 1. So in other words, we subtracted that coefficient 0.99 from 1. So next, it looks like body temperature is not significant. So we'll move on to the next parameter estimate. We'll look at our categorical predictor pain. So there's 3 levels here that are going to be compared to the mean of the base factor alert. And we can see here that as main effects, extreme pain, mild pain, and severe pain are all significantly different from the mean of the base level comparison group, which is alertness. And the B for extreme pain is negative 2.43. So this is where it gets a little more confusing, because the B for this categorical coded variable, so extreme pain, is the difference in the log odds of survival compared to that base, so compared to being alert. So for every single point increase in extreme pain, the natural log of the odds of horse's survival decreases by 2.43, comparing that to the log odds of the alert group, holding pulse and body temperature constant. So when we take the exponent out, in this case, so we dummy coded it. So we're getting an odds ratio that is relative to alert. Again, just to reiterate that point. So when we get 0.087, this means that for every single point increase in extreme pain, the odds of living decrease by 91% compared to alert, while holding all other predictors constant. And the B for mild pain is negative 1.41. So when we convert this one to an odds ratio, we get 0.245. So this means for every single point increase in mild pain, the odds of living decrease by about 76% compared to alert, while holding all other predictors constant. And this last one, the B for severe pain, is negative 2.63. So we convert that, we get an odds ratio of 0.79. So for every single point increase in severe pain, the odds of living decrease by 20.5% compared to alert, while holding all other predictors constant. It is interesting to see that we aren't getting a significant interaction effect with any of our predictors when we're looking at the interaction of body temperature with pain type. So when we run an interaction, we're seeing if the interaction has an impact over and above the prediction of, in our case, body temperature alone and pain alone. So the reason we're not seeing an interaction is likely because all the input variables are entered simultaneously in logistic regression. So there's probably not enough unique variance in our model to account for any interaction. So moving forward real quick, also we can use confidence intervals to test for significance. So this is the confidence interval for the logistic regression model, and we really want to exclude 1 from the interval to reach significance. So we can see that we're missing a 1 in just about everything except in intercept, pulse, extreme pain, mild pain, and severe pain, which falls pretty nicely with what we found in our regression output. So I just wanted to get that example. So back to slide 6. So we've gone through the results from logistic regression. Now we're going to see linear regression model on the right side. So we can see that the parameter estimates are looking a bit different from each other from the logistic regression model. So in comparison, we can't really trust the results of the linear model, even though we see that they are showing 1 or 2 significant predictors. This is because the dependent variable in our data is binary, and that means we're violating assumptions that linear regression must follow. And we're also seeing our standard errors, and we're getting residuals that are not interpretable. So in other words, OLS really isn't suited for binary outcomes. So even though we may have significant predictors, we can't trust this model because it doesn't fit our data well. All right, so just to reiterate that point, we can look at some diagnostic plots from the regular linear regression. So clearly we can see from our plots why using OLS is not ideal for this type of data. So our plots aren't looking so great in terms of heteroscedasticity, meaning that the variance of the residuals isn't constant across the range of the outcome. And also the residuals are not normally distributed. They have a bit more of an S shape going on, but it's honestly not the worst plot. But what we have done is we've absolutely violated the assumption that we have a continuous predictor because ours is a binary outcome. So in logistic regression, though, it is important to remember that we will have inherent heteroscedasticity. So for each value of predicted probability, we have a different measure of variance that's accounted for. And this is actually why we can't talk about variance that's accounted for in logistic regression like we can with the regular regression. This is also why we weren't given an R-squared value in that output in comparison to regression output, regular regression output, which does give us that. So here we can see a ggplot. This allows us to kind of convert probabilities by getting a prediction. And so what we're seeing is that these slopes are all probabilities. And we can see that there's definitely a relationship in that the predicted probability of living, or that y hat value, it is highest for horses who are alert. And then the probability of living is much lower for horses in extreme pain. So we can see that from that green line that's the lowest on this plot. So, this makes sense. So as level of pain increases, the predicted probability of living decreases. And we can also look at pulse on this x-axis to see that as pulse increases, for the most part, the predicted probability of living decreases. So implications. Overall, it seems like logistic regression was a better fit for our data, especially given the fact that we had a binary outcome variable, which violated a handful of Gauss-Markov assumptions, like non-normal distribution, for example. So when we do have non-normal distribution, Press and Wilson recommend that we use logistic regression with maximum likelihood estimators because this gives us a better fit for our model with this inherent smoothing process that it has. So we definitely saw that our standard error was much more inflated in the OLS model, which meant that inflated the p-value and made us less likely to reject the null. We had much more significance, less inflated error, and overall a more reliable model with logistic regression. So one other thing I want to note is that logistic regression really isn't all that helpful for us unless we are dealing with things like life or death. So in this case, we were, so that's good. But having a model that tests these discrete categorization of variables, it's not as generalizable for us in the real world. So it definitely has limited applicability and usage, but it can be really meaningful for things like this. And the last thing is that a great takeaway from the Friedman article is that the way you run your statistics doesn't matter as much as having a good design based on theory, relevant data, and also making sure to test those predictions to see if they have any external validity in the real world. So otherwise, we really can't make correct interpretations or conclusions, even if we have super complex models.